Hello. This is the fourth lecture in hypothesis testing. In chapter 9, we defined the decision rules for hypothesis testing, and we learned p-value, critical value, t-statistic, and when to make a decision. What is a significance level, and how can we reject the null hypothesis. And in the last lecture, I introduced new concepts of type 1 error and type 2 error. So I introduced there are two possible errors depending on whether the null hypothesis was actually true or not. If the null hypothesis was true, then you should not reject the null hypothesis, but if you do reject, then you are making the type 1 error. But if the null hypothesis was wrong, then you should reject it if your decision was correct. If not, if you could not reject it, then you are making type 2 error. And one important conclusion was that the significance level is always the probability of type 1 error. And we also learned type power, which is the probability of rejecting a wrong null hypothesis. So the power is also the probability. And also another important point was that it depends on the significance level. So as the significance level increases, you are rejecting more, so you are making more type 1 errors, but you are making fewer type 2 errors. Today we are going to talk about a totally different aspect of hypothesis testing. The hypothesis testing, the hypothesis we have considered so far always take this form. So I only considered the null hypothesis that the population mean equals to a value versus the alternative hypothesis that the population mean is different from the value. Then what we are doing here is we are going to reject the null hypothesis if the true mean is too small or too large, right? And so we have to calculate the p-value. P-value is the probability on the tail, so it has to calculate the left-hand side and the right-hand side tails. And critical values exist on both sides because you have to reject if too small or if too large. So always the being too small is is treated equally as being too large. Being too small, being too large are just symmetric. Everything else was the same. However, we are going to consider a totally different concept. By the way, the example, I did not introduce the example. It was a running example from the previous chapter. I did not introduce that, so just ignore what I'm doing here. So what we are going to do here is we are going to consider hypothesis of this form. So the null hypothesis is the same. However, we change the alternative hypothesis. So for example, the population mean is greater than 0 or smaller than 0. So it goes like this. The rejection happens only on one side. So you are rejecting the null hypothesis when the data is too large, too much larger than what your hypothesis implies. Or you may, if you change the direction of the inequality, your rejection region would be on the other side. So the point here is you are considering only one side, whether it is too large or too small. They are not equal anymore. So we call this one-tail test. One-tail test is when the null hypothesis is on inequality. So here I use this notation. So upper tail test, or we say upper tail test or lower tail test. And for upper tail test, we are checking mu is greater than something or not. So you believe that mu, the population mean, equals to something, but you have to reject it if it is too much higher than that. If mu was smaller than this, then you don't care. Not a problem. So often you may write the null hypothesis in this way. The null hypothesis may include inequality too. So the null hypothesis must include an equality always, but it may include inequality at the same time. But the alternative hypothesis should always have a strict inequality. A strict inequality is what you expect from the alternative hypothesis. Lower tail test is symmetric, but with different side, different direction of the inequality. In this case, you can imagine that the null hypothesis includes that implies that mu equals to a value or greater than that. So or greater than that can be omitted. It's implicitly automatically implied by the alternative hypothesis. So we are focusing more on the alternative hypothesis. We don't care this side. We only consider equality here for the null hypothesis, but inequality is important for the alternative hypothesis. So simple idea is like this. When you use upper tail test, you are going to reject the null hypothesis only when x bar is too large. And in the other case, when you have the alternative hypothesis as the population mean smaller than something, then you have to reject the null hypothesis when x bar is too small, too low. So this actually one tail test is more common in many examples, but I just wanted to introduce the two tail test first because that is more similar to the confidence interval we learned earlier. And we are going to learn more examples later, but here all the other ideas are the same. The only difference is exactly, so think about the example we considered the first. We considered free cancellation policy and cancellation abusers, abuse of cancellation, and we considered those who have too many large number of cancellations as suspicious, right? The suspicious customers are those who make large cancellations, many cancellations. But if there is like, for example, if a customer who never made a cancellation is not suspicious at all, right? Even if the probability of cancellation was 20%, making like smaller, like making fewer cancellations does not cause any problem. So we are not interested in them. So in that example, actually one tail test would be more appropriate. We are trying to find out the customers who are making too many cancellations. And from there, that's the starting point we considered. So from there, all the intuition holds in the same way. Like t-statistic is exactly the same because t-statistic is just the standardized difference between your hypothesis and your data. There is no difference in t-statistic, but the difference can be found in p-value and critical value. P-value, when you calculate p-value in two-tail test, your p-value was the probability outside of plus minus t statistic, right? Plus minus t. The probability greater than t, smaller than t, right? On two tails. But now, you don't consider two tails. You are looking at only one tail that you are interested in, right? So depending on the direction. So p-value only includes one side, one tail probability. Similarly, critical value does not need two values. Now, like previously, we are going to reject the null hypothesis if x bar is too small, sample mean is too small or too large, but now we don't care one of them. So if x bar is too small, I don't mind. That's totally fine. But if x bar is too large, then we are going to reject the null hypothesis. So you are going to see more examples, but the idea so what's important here is the idea we developed in chapter 9 in the previous chapter. So if you don't remember what I'm saying, maybe it is also a good time, another good time to review them before going into more detailed examples. So we are going to start from an example in the next video. So if you think you need some review, go review chapter 9 and continue watching the next video. See you in the next video. Bye.